Hello and welcome to my first lesson on area under a curve in integration. I've said the first lesson because I've split the lesson for area under a curve into two sections so that it's not going to be too long. And so let's begin right away. Area under a curve. As we begin this, allow me to say the following. 1. Area under a curve is normally estimated using the counting technique or the trapezoidal rule or the mid-ordinate rule. However, integration gives us the exact area. So area under a curve can be operated as though we are looking for area of an irregularly shaped body, and we can use those three techniques, the counting, trapezoidal or mid-ordinate rules. But if we want an actual value, we're going to use integration. And as we do that, as I explain that point, I'm going to use actual example as we go forward. So we are told find the area under the curve y is equals to minus x squared plus 7x minus 6. And I think it's a good idea that I do, first of all, by estimation using the trapezoidal mid-ordinate rule, and then we can try out with integration. For this particular question, I'm not going to use the counting technique. And therefore, let's begin with the trapezoidal rule. As we attempted using trapezoidal rule, I'm going to have the curve sketched, and so it is on your screen there. We have the curve y is equals to x squared minus x squared plus 7x minus 6, and we use trapezoidal rule, so we need to have some trapezia. We got 1, 2, 3, 4, 5 of them, and we know the formula for trapezoidal rule is half h in brackets the first height plus the last one plus 2 into all the others. That is the second, the third, up to the second last. And therefore, for the question that we're given here, the width between, that's the width of every trapezia, is actually 1. It's a unit. That is, from 1 to 2 is 1, from 2 to 3 is 1, from 3 to 4 is 1, from 4 to 5 is 1, again from 5 to 6 is again 1. The first and last heights are 0, because here the height is 0. Here again the height is 0 because the curve intersects the x-axis at that first point where we have the first height being 0, and the last point where we have the last height being 0. Again, all the other heights are 2, 6, 6, 4 respectively. This point is it's 4, 6, 6, 4 respectively. The first one here is 4. Just read the y-axis value. The next one is 6. Just move across. The next one is 6 again. The next one is 4. And so, replacing the values and operating, you're going to estimate the area to be 20 square units. That is just an estimate or an approximation of that. If we approach the same with mid-ordinate rule, we're going to have to sketch the same curve. I've sketched it again because I want to present to you how the mid-ordinate and trapezoidal rule are slightly different, although very similar. And so we have the curve again. We need to have trapezia, and I have sketched them for you there. Again, they're just 5 like we had here. However, we're going to need mid-ordinates for every trapezia. So for the first trapezia, this first trapezia here, we have a mid-ordinate. That's a line that is midway from 1 to 2, touching the curve at this particular point. We have another mid-ordinate for the second trapezia from 2 to 3, midway of that is around 2.5. You go up until you touch the curve, and the same thing for the next trapezia, and for the next, and for the last one there. The heights of the trapezia are given there: 2.25, 5.25, 6.25, 5.25, and 2.25. All of these values are read directly on the y-axis. That's where the mid-ordinate touches the curve. Just read the y value. Again, where the mid-ordinate touches the curve, move to read the y value, and the same for all the other trapezia. Therefore, now the rule, the mid-ordinate rule, is h in brackets the first height plus the second plus the third plus the all the way up to the last. For my case, therefore, I'm going to have height is 1. That is the width of the trapezia that are given. The distance from 1 to 2 is 1. 2 to 3 is 1. 3 to 4 is 1. 4 to 5 is 1. And 5 to 6 is 1. And the y's are 2.25, 5.25, 6.25, 5.25 again, and 2.25. And therefore, simplifying that, the answer becomes 21.25. This again is an approximation. If you want to improve your accuracy on trapezoidal or mid-ordinate rule, you need to have many more trapezia as it's humanly possible. For the sake of explanation, I've used the 5 trapezia for both of them. Let's move on to integration. And now this forms the bulk of the objective of this particular lesson. So let me say the following. If someone told us to look for the area bounded by the curve y is equals to x minus x squared plus 7x minus 6, and we already have the sketch of the curve as it is here, it is only gotten by, and accurately so, integrating the curve and include the limits 1 to 6. Right? That is a general rule. If we want to find the area under the curve under integration, we integrate the given curve and we use the limits here for the points where the curve touches the x-axis. That's generally the rule, and it's applied slightly differently depending on how the curve flows. But for a simple curve like the one we have here, we integrate the curve that's given, that's minus x squared plus 7x plus minus 6. The limits is from 1 to 6 because those are the 2 points where the curve touches the x-axis. So that rule is generally that way, although we'll adapt it as the question will require us to. Therefore, for this question, to get the integration, to get the area, we just integrate that. And integrating that, following the rules of integration, as we did in the definition, we integrate to get this particular integral here. The limits are 6 and 1, replacing the values. If you put x is 6, you get this particular bracket. Okay? And if you put the value of x here to be 1, you get this other bracket. And simplify further, you get the answer is 20.83 square units. Remember, this is an actual area under the curve y is equals to minus x squared plus 7x minus 6. These two others here are estimates. One of them is smaller than 20.83, the other one is bigger than it. And therefore, we have an accurate figure we can always we can use if someone wanted to get actual area. So that brings us to the introduction of what area under the curve is normally found using integration. You just integrate, give the given curve, and put the limits appropriately. Maybe to illustrate this further, I'm going to use another example. And so let's go to that. We don't find the area bounded by the curves y is equals to x squared minus 5x and y is equals to minus 2x squared plus 16x. Now, whenever you are tackling a question on area under the curve using integration, it's always prudent for you to sketch the curve. And so I have sketched it for you. And it's that one that's doping on your screen there. I have labeled them. This is the line, this is the curve, y is equals to x squared minus 5x. This is the one, y is equals to minus 2x squared plus 16x. So the area bounded by the two curves is the one that's got a deep pink. I hope that's a color actually. This color here, this area here. We have this area all the way up to where the two curves intersect, and then going up and to the origin again. To continue illustrating that further, I'm going to add more information on the graphs. And the first thing is, let's have the area that we have on the screen. Let's have it divided into 3 regions. The region P is the one that is above the x-axis, bounded by this particular curve, that's y is equals to x squared minus 5x, all the way through the other curve now, minus 2x squared plus 16x to the origin. So I hope you can see the area I'm talking about there, the area P. Then we have the area Q, the area below the x-axis, but above the curve y is equals to x squared minus 5x. Then there is another area R, which will help us in getting the area for P, and that area is from this point here to the point where the two curves intersect. There's a perpendicular, there are two perpendicular lines there, the x-axis and this perpendicular line, and then back along the y is equals to x squared minus 5x. Therefore, we have those 3 areas. It's essential for us also to get the other points which are necessary. One of them is where the two curves intersect. That is the origin and the point C. The origin is represented by A. The point C is represented by, sorry, the point C is the point of intersection of two curves. Again, it's necessary for us to get the point B, which is where this particular curve, x squared minus 5x, cuts the x-axis. That's necessary for us. I'm going to show you how that is necessary as we progress with the question. And therefore, first of all, someone will be wondering how to get the values for A and C, the coordinates for A and C. It's easy. To get the coordinates of A and C, those are the 2 points where the two curves intersect. So you're just going to say y is equals to x squared minus 5x is also equals to y is equals to minus 2x squared plus 16x. Therefore, just equate the minus 2x squared plus 16x and x squared minus 5x that way. Continue to simplify using the knowledge of quadratic operations, which is followed through there, and the answer should be x is equal to 0 or 7. That means wherever those two curves are intersecting, one of them is a value where x is 0, the other one is a value where x is 7. So the value here is 7. Again, we look for the coordinate of b by saying this curve here touches the x-axis at the point 0 and another point. That point is b. So just equate that to 0 and simplify again using quadratic concepts, and you get 0, x equals 0 or 5. So again, we have a 0, and we have a point b, the x value is 5. Now we progress and put the coordinates appropriately there. A is 0, 0, obviously. So if you put x to be 0 here, you get the value of y is also 0. B is along the x-axis. Everywhere along the x-axis, y is 0, and we know the x is 5, which we got here, so it's 5, 0. C is 7, y. I don't know what y is, and I don't care what it is because it's not necessary for us here. However, in an actual question, you might be told to find the coordinates of C, but if you are not asked, like in this case, you don't need to look for that. The reason I don't include it here is because I want to illustrate the fact that all we need is the x coordinates for integration, not the y's. Therefore, now we progress with the question. The area we're looking for is the area of P plus the area of Q. All right? And how do you get these areas? First of all, I'll need to find the area R. I'll need the area of R so that it helps me to get the area of P. So to get the area of R is in an integration of which curve? This line here. You see, it's an area under the curve x squared minus 5x from x equals to 5 to x is equals to 7. The 7 is the one we got here. And this is where we apply the values of x's we got, the 0, 7, and 5. So we are integrating the curve y is equals to x squared minus 5x from 5 to 7. That's what we have here. Follow the rules of integration. You get this integral. The limits are 5 to 7. Put the values of 5 and 7 respectively on the two brackets, which gives this bracket and this other one. And simplify that further, you get minus 49 over 6 minus negative 105 over 6, which is a negative 38 all over 6. That's the area of R. We move on to get the area of P, and it is the integration of the curve minus 2x squared plus 16x. You know, it's the area under that particular curve. So we're integrating that curve from 0 up to 7. But we subtract the area we just found there because it's not part of the area we want. P is anything else except that. So we subtract the R. So that's why I have that kind of integration there. So integrating that, you get this particular bracket here. Replace the value of x with 7. And again, replace the value of 0. X being 0. When it is 0, it reduces to 0. So we don't need that. I have this particular bracket, which is replacing the values of x here with 7, which gives us this, minus R, which is 38 over 3, and therefore the area will be this one here, which is simplified to 452 all over 3. That's the area of P. We need the value of the area of R of Q. Sorry, the area for Q is integration of. You see, it's below the x-axis but above the curve x squared minus 5x. So now that it's above that particular curve x squared minus 5x, it's going to be a negative answer. But you're going to ignore the negative value and use it as though it's positive, because normally area cannot be a negative answer. Again, the limits are from 0 to 5 because those are the 2 points where the curve cuts the x-axis. So integrating, and by the way, the reason I put this negative is so that I will not use the answer as it will be, as I'll get it. The answer I'll get here will be negative. So I put negative here so that I'll end up getting a positive answer. But you don't need to do that in an actual example. In an actual exam, maybe you just need to integrate, get a negative answer, and ignore the negative, use it as though it's positive. So integrating that, you get what you have here. Put the values of x to be 5 and 0 respectively. The 0 reduces to 0. The 5 reduces to 125 all over 6. Yes, 105 over 6 that way. And if you go ahead, you get the answer is just the positive of that. Remember, this is negative, but I've put a negative outside here so that it changes it to positive. But I've said you don't need to put this negative all through. This negative, which is also this one, you don't need to put it. You can just get your negative answer, which is negative 105 over 6, and ignore the negative and get your positive value. So the area for Q is that one. So I think we are almost done. The total area therefore will be the area of P plus the area of Q, which is what you have on the screen there. It's going to be 452 all over 3 plus 105 all over 6, which is 171.5 square units. And that brings me to the end of my first lesson as I introduce area under a curve. Hope you find it helpful. Please check this video along with the next one that follows or is done exactly the same time with this, which is going to help you in getting the concepts. Thank you. Always like, subscribe, and share.